So let's start off today's class with a discussion on how to essentially consider performance specifications during control design, right? So what we have done till now is that, like, we have looked at the plant or system block, we have also looked at the controller block, then we have seen how to characterize the plant or system for using mathematical models and basically obtain the transfer function of the system, and then how do we calculate the response or the output of the system for various inputs, right, standard inputs, and based on those inputs, like how to specify performance, right, or quantify performance parameters for various types of systems, right. And then we looked at stability. We figured out that for Bibo stability, we require all the poles to be in the left of complex plane, and essentially we looked at various choices for controllers that we have, and we did a few examples, right, on how to essentially control the closed loop system, right, and use the Rhodes criteria to get like ranges of controller parameters that would provide closed loop stability. Now the question arises as to how do we address performance, right. So the question that we are going to ask ourselves today is that how can we convert performance specifications into desired regions, let me put it like this, okay, of closed loop poles. Okay, so that's the question we are going to ask ourselves, right. So because we figured out that if I want closed loop stability, we need all the closed loop poles in the left of complex plane, right. Now the question is that, like, in addition to closed loop stability, I want to have some region in the left of complex plane where I should have my closed loop poles to lie, that would ensure that the closed loop performance specifications would be met. Okay, so that's what we are going to look at. Okay, so we are going to look at it from two perspectives. So essentially, I am just going to take an example and then and then demonstrate how can we do this. Okay, so let us consider an example, right. So let's say that it is desired that the dominant dynamics, let me put it in quotes, okay, dominant dynamics of a closed loop control system behave like that of an underdamped second order system okay, with a settling time of at most 4 seconds and a maximum peak overshoot of at most 10%. Okay, so let's say like this is what we have been given, right. So let's say I am told that design a closed loop control system for some practical application, right, such that the closed loop control system's dominant dynamics, right. So what do I mean by dominant dynamics in quotes? We have looked at what are called dominant poles, right. Dominant poles are those which are closer to the imaginary axis. So let's say I want my two poles which are closest to the imaginary axis to behave like those of an underdamped second order system with a settling time of at most 4 seconds and an maximum overshoot of at most 10%. Okay, so those are my desired requirements. Now the question is that how do I convert it into performance specifications. Okay, so let's do that. So so please recall that for an if we consider an underdamped second order system and we did all the derivations, right. So the settling time Ts was essentially corresponding, of course, corresponding by default to the 2% settling criteria, was equal to, what is the formula for the settling time? It is going to be 4 by zeta omega n, right. So 4 by zeta omega n was the expression for the settling time of an underdamped second order system, considering the 2% settling criteria, right. So let's say, like I want this to be at most 2 seconds, right. So this immediately implies that zeta omega n should be greater than or equal to 2. This implies that minus zeta omega n should be less than or equal to minus 2, right. So recall that the real part of the poles of an underdamped of an underdamped second order system was, what was the real part of the poles of an underdamped second order system? We looked at an underdamped second order system, right. What were the two poles? Minus zeta omega n plus or minus j omega d. Oh, okay. Oh, sorry, I made an error here. Okay, sorry. Okay, did I? Okay, if I said 4, kindly change it. Thank you. No, sorry about that error. Is this correct? So minus zeta omega n should be greater than, should be less than or equal to minus 1, right? Yeah. Okay. So recall that the real part of the poles of an underdamped second order system was, of course, is, right, minus zeta omega n, right. So what this essentially means is that if I have my dominant poles to have a real part which is less than minus 1, I can meet the settling time criteria, right. So that's what this calculation concludes, right. So let's draw that, right. So let me draw the S-plane and let's discuss this, right. So let's discuss what we just wrote down. So let's say, like I want to have, I'm drawing the S-plane, right. So the real axis and the imaginary axis, okay. So this is the left of plane and this is the right of plane, okay. So this is something which we already know. So so for stability we need all poles in the left of plane, right. So that's something which we already know. Now the point is, let us say, like I look at minus 1 and draw a vertical line passing through minus 1. Okay, let me say I draw a vertical line which is parallel to the imaginary axis at minus 1, right. So what this expression means is that if I have my dominant poles to be to the left of this line at minus 1, right, passing through minus 1, then I know that my settling time is going to be less than 4 seconds, right. So that's what we can conclude from this analysis. So this region to the left of this vertical region essentially gives me an assurance that the settling time is going to be less than 4 seconds, okay. So that's the region which will satisfy the condition on settling time. Is it clear how we concluded it, right? So we concluded it from this analysis. So we can immediately see that for closed loop stability we need all closed loop poles in the left of complex plane. Now what we have done is that we have constructed a subregion of this left of complex plane in which I want my closed loop poles to lie, right. If all my closed loop poles lie in this region, then I am assured that my closed loop system settling time would be less than 4 seconds. Okay, so that's what we have figured out, right. Now let's use the second criteria, okay, of maximum peak overshoot, right, maximum percentage overshoot. So, yes, please. It is desired that the dominant dynamics, okay. It's not, see, the closed loop control system may be of order 10, for example, okay, it need not be second order. Okay, what we are saying is that, see, in order to get a meaningful what to say engineering solution for design, given that we are having some quantitative performance requirements, how do we convert it into something which we can, through which we can process the what to say location of the closed loop poles. That's what we are doing. Okay, so by and large, like even for a higher order system, by and large, like we desire that the dominant dynamics be like that of an underdamped second order system. Should be, yes. So we are going to complete this region. We will come back once again, right? Of course, see, as I took an example, let's say we have a 10th order system, right? There can be 2 dominant complex conjugate poles, there may be 8 other poles, right, which will lie somewhere nearby, that's fine, okay. But we are just converting it into a region, right. So the second specification is on maximum peak overshoot, right. So the maximum peak overshoot was e power minus zeta pi divided by square root of 1 minus zeta squared, right, times of course 100%, right. So this should be less than or equal to what number did I choose? 10%, right. So that's what I have chosen, right. So this implies that e power minus zeta pi divided by square root of 1 minus zeta square should be less than or equal to 0.1. Okay, can you process this and get me an inequality in zeta? So this should give me some condition like zeta should be greater than or equal to. So of course, how do you do it? First take natural logarithm on both sides, right? Okay, and then like just cross multiply square and then get the value. Of course, since zeta cannot be negative, we only take the positive value, right? Yeah. Of course, always please remember we talk about performance specifications only after we figure out stability, right? Without closed loop stability, like it is not meaningful to talk about performance. Okay, so by default, when we are talking about performance, we should have already checked stability. Okay, so that's something which we need to bear in mind when we do control design, right? Yeah. Yeah.
If this is say a 10th order system, then we cannot model the settling time as 4 by 2.
I agree. Okay, but what we are saying is that if we design all the 10 poles to be to the left of this -1 line and you subject it to a unit step input, you get a reasonable engineering guarantee that the settling time criteria will be met. That's the guarantee, right? Okay. Yes. What is the condition that we get on zeta? See, you take the natural logarithm, and yeah, I'm sure you can calculate it, right? So how do we get a calculator here? So, oops. So let's say you just first take natural logarithm of 0.1, right? Where is ln? Okay, so it comes to be -2.3. Of course, then you just can multiply it by -1. Okay, and then we just need to square it. Okay, So squaring it, then we have we can just take 1 by x. Okay, let me do it in my own way. You please do it and let me know whether I am doing it correctly. Okay, multiply by pi. So that gives me this much theta square plus 1, and I take 1 by x, and we take square root. I think I did something wrong here. What value do you get? Take the natural logarithm. This you get. Point 5911. Am I correct? Okay. So that's what we get. So 0.5911. Okay. So of course some simple algebra. I just did it in the calculator. Okay. So I'm sure you can figure it out. Take the natural logarithm on both sides and cross multiply and then square the inequality. Then what you will get is that like you will get a equation in zeta squared, right? You won't have a zeta term. So you can get a condition on zeta squared, take the square root, then you will get a condition on zeta, right? So zeta is 0.5911, right? So if you recall what we did when we discussed the second order, underdamped second order system, you recall that zeta was related to an angle called beta, right? What was beta? Beta was the angle made by the two poles with the negative real axis, right? When I draw a line from that pole to the origin, right? And what was the relationship between zeta and cos beta? Sorry, zeta was cos beta, right? The relationship between zeta and beta was cos beta, right? So cos beta must be greater than or equal to 0.5911, right? So that's what we get. Okay. So this implies that beta should be less than or equal to what is the cos inverse of 0.5911? So it's going to be 53.76, right? Am I correct? So if you take the cos inverse of 0.5911, it is going to be 53.76 degrees. Okay, so this is what we have. So what does this mean? So you recall how we can get graphically visualize beta. So let's say I draw sort of an open cone, okay, and I make this angle as the beta which we calculated, 53.76 degrees, okay, on both sides of course. Okay. So what this means is that as long as my poles lie in this cone, right, I can satisfy the constraint on maximum peak overshoot, right, because the maximum peak overshoot constraint we have converted into an constraint on the damping ratio zeta. And how do we graphically visualize the damping ratio in the complex plane? By using this angle beta, right. So as long as my beta is less than 53.76 degrees, right, I can be assured that my maximum peak overshoot is going to be less than 10%. So I would want all my poles to lie in this cone, right, okay, whose tip is at the origin and which makes an angle of 53.76 degrees with the negative real axis, right. That assures me that the maximum peak overshoot criteria can be met. Okay. Now I want to meet both conditions, right. What should I do? So essentially let me mark it. This essentially ensures that MP is less than or equal to 10%, right. So that is this region, right. So So, if I want to meet both the conditions, I have to take the intersection, right, of the two regions, right. So, and what is the intersection of the two regions? Let me draw it. Okay. So, that is going to be like an open trapezoid, right. So, which will be okay. So, that is going to be the intersection of the two regions. Okay. So, as long as I place my closed loop poles in this region, all right, what is shaded in pink. So, I am assured that I can guarantee I will be guaranteed both conditions on settling time and maximum peak overshoot, right. So, that is the manner in which we have converted conditions on performance to a desired region of closed loop poles. Okay. So, that is what we have done, right. Of course, please note that we can place the closed loop poles anywhere in this region. Okay. So, many times like people try to place them right at the apex or these 2 points, okay, the two what I call as nodes, right, of these open trapezoid, okay, but that is not necessary. Okay. So, you can place it anywhere within this open trapezoid. Okay. So, then our conditions on performance requirements will be met, and please note that this feasible region is a subset of the left off plane, right. So, kindly note that we always talk about stability then performance. So, if you place if we place the closed loop poles in this desired region, we are anyway we guaranteed stability, because anyway it's a subset of the close left off complex plane, right, which assures closed loop stability. So, that is something which we need to remember, which we can easily observe. Okay. So, this is one example, right. So, of course, this makes our job a little bit challenging, right. So, now the question is how do we what design process do we make, do we adopt, to make sure that all our closed loop poles lie in this open trapezoidal region, right. So, see, for till now, if we just did a few examples where I just wanted closed loop stability, wasn't it. So, then we used the Routh's criteria and then like figured out, looked at the closed loop characteristic polynomial and then like figured out what conditions on the controller parameters would give me all roots of the characteristic polynomial to be in the left off complex plane, right. So, we could easily do that, right. Now, like we want to essentially have conditions on the controller parameters which would place my closed loop poles in this desired region. Okay. Then what tools do we use? Okay. So, that is something which we are going to study from let us say the next in the next class. Okay. We will use what is called as a root locus methods. We will learn what is meant by root locus, and then like we will figure out how we are going to use this for control design. Okay. So, that we can meet both stability and performance. Okay. And in fact, such an idea can be also used to evaluate what is called as relative stability. Like see there are broadly like two notions. What we have been looking at is what is called as absolute stability. Some people would use the adjective absolute before stability, because to just convey that like we want before stability and all poles to be in the left off complex plane. Okay. So, what is meant by relative stability? Like yes, we do have stability, okay, but then as we told, we do not want to be too close to the imaginary axis, right, because there can be unmodeled dynamics, there can be parametric variations and so on, right. So, the locations of the poles may change a little bit. So, then what happens is that like we introduce what is called as relative stability, which we will revisit later in this course, right, that look, I do not want my poles to be in the left off complex plane, but I do not want them too close to the left off complex plane. I can say, for example, that place all my closed loop poles to the left of minus 0.5, for example. Then what am I doing? I am drawing a virtual line, vertical line at minus 0.5. I want all my closed loop poles to be in that region. So, I have offset the region, right, desired region. Okay. Now, how can I handle it? I can handle it using what we will learn as root locus, and we can also handle it using other methods, right. So, can you think of how we can still use Routh's criteria and try to see whether I can place all my closed loop poles, say for example, to the left of minus 0.5? You just need to shift the imaginary axis, right. You just need to define an S hat and then shift the imaginary axis and rederive the characteristic polynomial and apply the same Routh's criteria. Okay, anyway, we will do all these things later. Okay, but think about it, right. See, if I want relative stability, I want all poles to be to the left of minus 0.5, for example, like what I would do is the following, right. So, if I have my real axis and my imaginary axis, and this is my S plane, right, I say that place all my poles to the left of minus 0.5, okay, for assuring relative stability. So, this is S. So, if I define a variable called S hat, which is defined as S minus 0.5, what will happen? The imaginary axis in the S hat plane will be shifted to the S equals minus 0.5 line. Then your closed loop characteristic polynomial, wherever you had S, you substitute S equals S hat plus 0.5 and then use the Routh's criteria, right, for S hat, right. So, essentially you get a polynomial in S hat, apply the same Routh's criteria and figure out the controller parameters which will ensure that the values of S hat will have negative real parts. Then you are assuring relative stability in the original S plane, right. So, as I told you, like I am just preemptively introducing these concepts, like we will anyway revisit them later, okay. We will figure out how to ensure relative stability in our designs, okay. So, but then try it out, right. So, I will give you a simple example exercise to do. So, let us say our closed loop characteristic polynomial was, let us say, like S squared plus Kp minus 3s plus 2, right. Okay, this is the closed loop characteristic polynomial. Why don't you try for this polynomial, like for stability, for absolute stability, what do we need? Kp must be greater than 3, right, because this is a second order polynomial. I want all coefficients to be non-zero and of the same sign, right, for all two roots to lie in the left of complex plane, right. So, for absolute stability, Kp should be greater than 3, right. So, find the range of Kp to ensure relative stability as desired above, right. That is, let us say I want all my poles to be to the left of minus 0.5, what do you do? Okay, so, substitute S equals S hat plus 0.5, evaluate for S hat, right, and then like let us see what happens. Okay, why don't you try it out? Okay, so please try out as homework and let me know. Okay, so now you will see that the values of Kp will be different, right. So, the range of Kp will be different, right, that will ensure this relative stability. Okay.